What actually happens inside your GPU when you overclock it? I analyzed 45 sources from hardware engineers and real overclockers to break down the science that most tutorials skip over. In the next 6 minutes, you'll learn why voltage matters more than clock speed, what the silicon lottery really means for your specific card, and whether that 5–15% FPS boost is actually worth the trade-offs. I've compiled data from Tom's Hardware, Gamers Nexus testing, manufacturer documentation from NVIDIA and AMD, plus dozens of real overclocker experiences from Reddit and overclock.net forums. No sponsor bias here, just the technical facts you need to make an informed decision. Let's start with what's physically happening inside your GPU when you push that slider up in MSI Afterburner. Your graphics card processes data in cycles. Every frame you see, every texture loaded, every shader calculated happens in discrete clock cycles. When you overclock, you're literally forcing your GPU to complete more of these cycles every second. Manufacturers like NVIDIA and AMD set conservative clock speeds for a reason. They need every single unit they ship to work reliably. Not every chip that comes off the production line is equal, and they have to account for the worst performers in the batch. This means your specific GPU might have headroom the manufacturer couldn't guarantee across all units. Here's something most tutorials don't mention. Every modern GPU has a hidden voltage frequency curve that determines its behavior. This VF curve is essentially a lookup table. It tells your GPU what voltage it needs to run stable at any given frequency. When you overclock, you're working within these boundaries whether you realize it or not. Real overclocker insight from the forums. Users consistently report that their identical RTX cards can vary by 70 MHz or more in stable overclock potential. Your friend's exact same GPU model might hit different numbers than yours, and that's completely normal. Now here's where most overclockers get it wrong. They focus on frequency, but voltage is where the real physics comes into play. Power consumption scales with voltage squared. That's not a typo. A 10% voltage bump doesn't mean 10% more heat, it means roughly 21% more power draw and heat generation. This is the inescapable physics of silicon. Higher frequencies require higher voltages for stability. Your GPU needs that extra electrical push to switch transistors fast enough. More power flowing through the chip means more heat, and heat is what triggers your GPU's self-protection mechanisms. Thermal throttling happens in stages. Between 65 and 75 degrees Celsius, you're in the normal boost clock range. Everything's fine. Push to 78 to 82 degrees C, and you'll see minor performance reductions. Hit 83 to 87 degrees Celsius, and active throttling kicks in, costing you 10 to 15% of your performance. Above 88 degrees Celsius, your GPU goes into emergency mode, and may even shut down to protect itself. The forum consensus from overclock.net is clear. Voltage kills chips, not frequency. For 14 nanometers chips, the community generally recommends staying under 1.35 volts for long-term use. Push beyond that, and you're trading GPU lifespan for performance. So what do you actually get from overclocking? Some YouTube thumbnails would have you believe you're doubling your FPS. Multiple sources confirm the reality. Expect between 5 to 15% FPS improvement from a GPU overclock. Not 50%, not 30%. 5 to 15%. Tom's Hardware testing and countless forum benchmarks land in this same range. Clock speed increases of 10–20% are common, and GPU overclocking gives roughly linear FPS returns. Memory overclocking can add another 5 to 10% on top of that, but only in memory-bound scenarios. High-resolution gaming with heavy texture work benefits most. Factory overclocked cards like the EVGA FTW3 or MSI Gaming X Boost from around 1635 MHz to 1770 MHz right out of the box. Manual overclocking essentially does the work they already did. Here's a fact that explains forum arguments. Semiconductor manufacturing yields only about 30% perfect chips. The rest have minor defects or don't hit the highest targets. These chips get binned. The best silicon goes to premium SKUs. But here's the thing. You might have hidden potential in a budget card just because the manufacturer needed inventory. Gamers Nexus tested 7 identical GTX 1070 Ti cards and found over 70 MHz variance in maximum stable overclock. Your card's hidden potential is literally programmed in at the factory. Now for the part most guides skip. Electromigration is a real phenomenon where electrons literally push metal atoms around inside your chip over time. High voltage combined with high temperature accelerates this process, gradually degrading your GPU's circuits. There are 3 main killers: silicon electromigration, capacitor dryout, and fan failure. Tom's Hardware confirms GPUs are designed for 8 to 10-year lifespans under normal use. But real users report cards can lose headroom after 5 to 6 months of aggressive settings. That stable 2100 MHz might only hit 2050 MHz after extended abuse. Counterintuitive fact: crypto miners often treat GPUs better than gamers. They undervolt and run steady. Gamers thermal cycle constantly, which causes more wear. So what's the honest verdict? Overclocking is real physics with real trade-offs. You're trading heat and lifespan for 5 to 15% more performance. Voltage is the danger zone. Safe practices: stay under 85 degrees Celsius, keep voltage within limits, and use proper stress testing tools. For most gamers, the gains are modest but essentially free. If this breakdown helped, hit subscribe for more no BS tech explainers. Drop a comment. Have you overclocked your GPU? See you soon.